There are a number of situations that can be modeled by a search function, such as this one over here. It usually contains two t's. The t represents the time, and so it therefore must always be greater or equal to 0. This function also has a value for a, which is a positive constant. It also has a value for b, which is also a positive constant. So a search function is a function that can be used to model the behavior of a system when the response to a stimulus increases rapidly, such as drugs, in the beginning, and then drops off slowly. This type of function rises up to a maximum here and is followed by an inflection point. In this video, I want to prove that a local maximum occurs at that value 1 over b, and also I want to prove that the point of inflection occurs at value 2 over b. And I want to also show you that the distance to the global maximum is halfway the distance to the inflection point. So to prove that this function has a local maxima at 1 on b here, we need to show that the slope of that at that maximum is equal to 0. So therefore we need to differentiate this particular function first. As I said, because there are two t's in this function, we're going to have to divide them into two parts and use the product rule, where u is going to be at and u dash will be a, and v is going to be e minus vt, and v dash e minus bt multiplied by negative b. And substituting them into this particular function, we will have, and this could be tidied up really quite nicely into a negative from the minus b again. Now you can see that you've got EBT here, and also you've got EBT here. As well, you have an A and an A. So we can factorize that. And by taking out the A and the E minus BT, we're left with
1 from the first term and TB from the second term. And this is a slope function, which we can find out what the value for the global maximum is by making it equal to 0, because the slope at the global maximum is going to be 0. And I'm going to write these terms individually. A, e to the minus bt, and then I'm going to write 1 minus tb is equal to 0. Now we know that the a is a positive constant, so we cannot use it. Let's have a look at e minus bt. You should know that e terms will never ever equal 0. So we're left with 1 minus tb. And if we rearrange that, we'll get that's 1 equal to tb, and therefore t is equal to 1 over b. So the global maximum of this function is going to happen at time 1 over b. And the point of inflection will happen when the second derivative function of this is equal to 0. To look for the second derivative, I'm going to use this function, first function, and write it down here, f dash t. So the first part is easy enough to derive, but the second part here is once again made up of two sections. So one and then this one here. So to differentiate the whole thing, let's do the first one, a e to the minus bt multiplied by ab minus ab. And now we're going to do the second part of it over here, which will be basically u dash v plus u v dash, where u equals a, t u dash equals a, v equals b e minus bt, and v dash equals, which can be simplified into minus b squared e minus bt. Now we just need to substitute this and tidy up a little bit. So that's minus ab e to the minus bt minus everything inside the brackets. We'll start with u dash. So we have a. So what can we do now? I would just rewrite the whole thing from inside the brackets. We'll just have a b e to the minus bt minus a b e to the minus bt. So this minus over here and this minus over here will make this a plus. So that is a plus ab squared t e to the minus bt. Can you see that this term is exactly the same as this term? So straight away I can say that these terms could be just added together. So I have two of these, a to the b, e to the minus bt. And let's rewrite this one again here, t e to the minus bt. And if I remove the EBT out, as well as the 1b here and 1b here, as well as the a and the a in here, I could rewrite, and I'm left with minus 2 plus, there's 1b left there, t. And once again, we know that a is positive and b is positive as well. And we know that e cannot be 0. So it only leaves us with this orange part here where we can equate that to be 0. And we find the value of t to be 2 over b. And this happens when f dash t is equal to 0. The point of inflection is going to occur at t is equal to t over b. Now let's look at the graph itself at the very top again, and you notice that this part, as we said, was 1 over b, and this is 2 over b. So it can be deduced that this length over here is the same as this length over here. Also, by substituting the 1 over b into this function here, you will get the y value as a over b e to the minus 1, and you can also find out the y value of the point of inflection by substituting 2b into that function.